We looked at different parts of how to design routing algorithms, so some design decisions that need to be made when you select a routing algorithm. And we started yesterday looking at fixed routing. And we finished with some quick examples of routing tables. So we'll come back to routing tables because they're used in fixed routing and adaptive routing. So we're just going through 3 different strategies for routing. Strategy 1 and strategy 3 are very similar. Fixed routing, we choose the routes when we build the network. Strategy 3 is adaptive routing. We choose the routes when we build the network and we continuously update those routes. They adapt according to the changes in the network. The second strategy, flooding, is slightly different, and we'll go through that after we go through strategy 1 and 3. So fixed routing, we build the network, and because we build the network, we know the topology of the network, we know where the nodes are, we know which nodes link to which other nodes, and we know the costs of the links. Okay? If the costs represent financial cost, when we build the network, we know how much it costs to send data between 2 nodes. So given the network information, we can apply, for example, Dijkstra's algorithm and find the shortest path from one node to every other node. And that's what the handout gives you. Rather than you having to calculate the shortest path, it's just I've quickly this morning calculated the shortest paths. So in the table on the left, this side, it's a bit condensed, but what you see here with source node 1 for this example network, there are 6 rows in the table here. They are the path from source node 1 to each of the destination nodes. In fact, it also includes node 1 as a destination. So the first row here means from node 1 to destination 1, what is the shortest path? Well, we're immediately at node 1, so that one's not so useful. But the second row is from node 1 to node 2. The shortest path is from 1 direct to 2, and the cost of that path is 2. That's how you read the table. From node 1, the source, to destination 6 is the last row in that table, and we know from our examples yesterday that the shortest path is from 1, 4, 5, 6, the least cost path, and the cost of that path is 4. So that's for all of the source nodes and all the possible destinations. So we see that in the last, at the bottom of this table, source node 6, to reach node 1, the path is 65421 and the total cost of that path is 10. Saves you calculating, we can refer to that later. The second table we'll come back to later in the lecture. So in fixed routing, we calculate those shortest paths, the least cost paths from every source to every destination, and then store them somewhere. It depends whether we're using a centralized approach or a distributed approach. We can store them in some special central node or store them distributed across each of the nodes in the network. We'll see those two examples in a moment. Then when we have packets to send, when node 1 has packets to send to node 6, it just uses that path information to work out who do I send it to next. Node 1 will look up in that information about the paths. If the destination is 6, the next node is 4 and send it to 4. Node 4 will use that information. If the destination is 6, the next node is 5, and so on. Fixed routing is applicable when we have small networks, tens of nodes maybe inside SIT, when things don't change much, okay? Because we only set the paths at the start. Possibly if there's some major change in the network, we can recalculate the paths. But that may be on a weekly basis, not so often, not on a minute or even a second basis. We'll see the alternative, adaptive routing, strategy 3, automatically updates the paths on a regular basis, every minute or every several minutes, for example. Whereas fixed routing, it's fixed for some, days, weeks normally, the routes are. It's simple. You just configure the routers, you configure the nodes, the routes in the nodes at the start of the network, and nothing else to do. The packets, when they're sent through the network, the switches just look at the path information to determine where to send it. It's not very flexible in that when the network conditions change, maybe there's a lot of packets starting to be sent across this link. If the cost metric represents delay, then that metric will change over time. It may go up. With fixed routing, it will still use that link even if it becomes the suboptimal path. Okay? So it cannot adapt to changes in the network very quickly. Strategy 3, we can adapt. Okay? Before we get to strategy 3, how do we store this path information? And that's where we finished yesterday. For example, for node 6, we can calculate the paths from node 6 to each of the destinations. We can calculate the total cost. But we don't need to store the entire path. In fact, the only thing that we need to store is the next node in that least cost path. Not only is the storage simpler, but also we don't need to know about the rest of the path. Let's consider an example on the board for the path from node 6 to node 1. And I've written it on the board here. The least cost path from 6 to 1 is 65421 with a cost of 10. The link costs are shown on the board here. So with this path, if this is the least cost path, we know immediately that a least cost path from node 5 to node 1 must go through 4 and 2. Okay? Because, and we finished yesterday, that if there was an alternate path from 5 to 1, let's say we had another node in the network, node 7, if there was another node in the network with a path to node 1 with a cost of, say, from node 5 to node 7, 2, and node 7 to node 5, node 7 to node 1 had a cost of 3. If that was true, then there's a path from node 6 to node 1 with a cost of 9. The top path has a cost of 10, a total cost of 10. If there was a path from node 5 to node 1 with a cost less than 6, then it means there's a path from node 6 to node 1 with a cost of less than 10. Because the cost of the path from 6 to 1 is simply 4 plus the cost of this path, which is 6 here. So if we had a path from 5 to 1 less than 6, at a cost of less than 6, then it means there is a shorter path from 6 to 1. But so on the other hand, if we know a least cost path from 6 to 1 has a cost of 10 and goes 5, 4, 2, 1, then it implies that a path from 5 to 1, the least cost is 5, 4, 2, 1. And similar, the least cost path from 4 to 1 is 4, 2, 1. And from 2 to 1 is 2 to 1, using the same principles. So in fact, from node 6 perspective, there is no node 7 in the example network. But from node 6 perspective, all it needs to know is that it has a link cost to node 5 of 4. if node 5 tells node 6, I have a path to node 1, and the cost of that path is 6, and that's the least cost path to node 1, then node 6 knows the cost of its path to node 1. It's 4 plus 6, 10. And now let's introduce a different node. Let's get rid of 7. Let's say seven again. Let's say node 6 had another link to node 7, where it had a cost of 4. Then what node 6 needs to know in order to find the least cost path to node 1 is it asks its two neighbours, 5 and 7, what are your least cost paths to node 1? Node 5 has a least cost path to node 1 with a cost of 6. Let's say node 7 has a path to 1 with a cost of 8. Then, without knowing the path, node 6 can determine its least cost path to node 1. Because it's simply either 4 plus 6, which is 10, or 4 plus 8, which is 12. So the least cost must be via 5. So 4 plus 6, the least cost path is via 5. So importantly, node 6 doesn't need to know about the path from 5 to 1. It just needs to know that node 5 leads to the least cost path to 1. That's why node 6 only needs to store the next node in the least cost path. And in fact, when it needs to discover information about paths, really it doesn't need to discover who's between 5 and 1, it just needs to discover the cost of the path from 5 to 1. And then it can determine its least cost path to 1. So we don't have to know about the entire path in the network. And this becomes important in practical networks when we have large networks and the nodes need to collect information about all the least cost paths. Rather than collecting information about the entire path, it just needs to collect information about the links to its neighbours and the costs, their least cost paths to some destination, and in particular the cost of that path. So it simplifies the management of the information about the least cost paths in the network. So on this diagram we show the complete path. Instead of storing that complete path, each node stores just the next node in the path. Node 6 would say to reach 1, the next node in the least cost path is 5. Node 6, to reach node 2, the next node in the least cost path is 5. So the second column in this table here is what's stored in each node. And that's where we get our routing tables. On this handout, so focus on the second column for each node, and we see that's, going back to the slides, what our routing tables come from. This is the case node 6. To reach destination 1, next node is 5. To reach destination 2, next node is 5. And in this case, the next node is always 5 for node 6. For node 1, the next nodes are stored here. This is our routing table, and it's used to determine where to send our packets to. When we have a packet, we just look at the destination of that packet, the destination address, look it up in the first column, and it tells us where to send it to, which neighbour to send it to. And if these tables are created in this way, then the packets will flow across the least cost path to the destination. This approach is a distributed approach where each node stores this routing table. Node 4 stores this table. Node 5 stores this table, and so on. The previous slide is a centralised approach. Let's say we have one special node, node 0, which is also in the network. And it stores all of that information, the routes from, or the next nodes from any source node, the column, to any destination. So if a packet is coming from node 3, or is at node 3 and it needs to go to node 4, the next node is 5. That's how we read that. In fact, this table is just a combination of the distributed tables. It's the same information. Look at the first row. From node 1 to nodes 2, 3, 4, 5, 6. Sorry, the first column. From node 1 to 2, 3, 4, 5, 6. Next nodes are 2, 4, 4, 4, 4. That is simply the first table here, this. And the next column in the previous slide is the second table here. That is this information. So we can either store the information on one special node, a centralized approach, or more commonly today, in larger networks, store it distributed across each of the nodes, which is this approach. So these are called routing tables. Routing directories also used. A node determines the least cost paths to destinations. There's no need to store the entire path. We only need to store the next node in the path. And optionally, we can store the cost of the path. In practice, we may store also the cost when we later update things. So in general, the routing table looks like this. To reach, for a particular source node, to reach some destination node, what's the next node in the path? And optionally, what's the cost of that path? We don't absolutely need the cost, but it's commonly stored. And it may be stored in a centralized approach or a distributed approach. And that's on the next two slides. And now we distinguish between routing and forwarding. The process of creating these tables, putting the information into the tables, we'll refer to as routing. That is, finding the least cost paths and then populating these tables with data. That's normally the role of a routing protocol. Once we have the tables, to send packets, all we do is we look at the destination address of that packet and then look up in the routing table to see who is the next node I send it to. That we'll call forwarding. Forwarding the data packets through the network. So we distinguish or separate between the two phases. Discovering the routes, creating the routing tables, and then using the routing tables to send data packets through the network, being forwarding. And in the internet, separate protocols are used for each of these phases. You'll see in exams, past exams, and in the upcoming quiz, common question, create a routing table. So, given a network, such as this, create the routing table in a distributed approach for node 4, for example. So your steps would be, from node 4, what are the least cost paths to each possible destination, to node 1, 2, 3, 5, and 6. You need to find the paths. And then in the path, what is the next node in that path, and store that in the routing table. So, for example, the least cost path from node 4 to node 5 is in fact direct to node 5. So in the routing table, we'd say, to reach the destination 5, the next node is 5. I think you'll find also, to reach the destination 6, the next node is, which node in this case? From source 4, if the destination is 6, the next node in the least cost path is 5. Because we know a least cost path from 4 to 6. We know a path from 1 to 6 is 1, 4, 5, 6. So a path from 4 to 6 is 4, 5, 6. 1 plus 2 is 3. And similar for the other destinations. I think in this case, to reach node 1, the least cost path is node 2, node 1. A total cost of 5. So the next node is 2. So you can create the routing table based upon the path information. And you get the path information from applying some algorithm or just manually looking at the network to calculate the least cost paths. Any questions on routing tables so far? They are a key part of the internet. The distributed routing tables, where they're stored on each node, is more common than a centralised routing table, but both are possible. Has anyone seen a routing table before? These, we've been talking about switched networks and these being switches, but in the internet, most devices, including hosts on the internet, also have a routing table. Let's see if we can see it on mine. Don't want that. Where are you? Doesn't look. This is the routing table for my laptop. So in the internet, hosts, laptops, PCs normally have a routing table, as do the switches in the network. Except for hosts, it's usually much simpler. We're not going to explain the address formats, but there are two columns here that correspond to the key parts of the routing protocol. Destination column, and the gateway in this, the terminology for gateway means the next node in the path. So what it means, when my laptop wants to send to some address that matches, if we look at the second row, some IP address that matches 10.10.96.0, then the next node is this special all zeros address. We'll return to the structure of that later. There's other information that's also stored in practice, but this is just a quick example that our hosts have routing tables where we have destination and next node, except in this case there are some special cases for the next node. Sometimes we don't have a next node, we use a default, or we use a direct link, which is what the star or this all zeros is representing. But your hosts have routing tables. And simply when my laptop has a packet to send, it looks at the destination address of that packet, finds the matching row from column 1, and sends it to the destination according to what's in column 2. It's just that how to read that requires some further explanation. The rest is some supporting information about that route. One of them is a metric, a cost for that route. So there's some cost assigned which would allow us to choose, if we have two possible routes, we can choose the least cost route in that case. We'll come back to that maybe in a later lecture, and especially next semester in the lab. Routing tables are used not just in fixed routing, but in the next strategy, adaptive routing. So they're quite important. And again, we find the routes. In the phase of routing, we find the routes, find the least cost paths, and then put the data inside the tables. And when we have data to send, we use the phase of forwarding by simply looking at the routing table and determining the next node to send it to. In summary, with fixed routing, coming back to those design decisions that we looked at, when is a decision made for a route? Well, when we build the network, when we start the network. So in fixed routing, we just build the network, choose the routes, and choose them once. Who chooses the route? We can use either a centralized or a distributed approach. Either of them can be used. Where does the network information come from? From all nodes. That is, we collect information from all nodes, the costs of all links, and then choose the least cost paths. That's easy when we have a small network and when we design the entire network. It's not so easy if the network is large and if we do not know about some parts of the network. So in practice, only used for small, stable networks when things don't change much in the network. When do we update? Well, never in theory. In practice, we may update when there's a major change, maybe on some node is turned off or is disconnected from the network. Not very flexible. When we have larger networks, more than tens of nodes, then we need to be more flexible and dynamic. And we'll skip strategy 2 for now, we'll come back to it. So instead of fixed routing, adaptive routing. Same approach. Use a least cost routing algorithm to determine routes, but as the network conditions change, adapt and update those least cost routes. So if something changes in the network, recalculate the least cost paths. And this is what's used in most packet switching networks, at least large ones, and in particular in the internet. Same approach, we still use routing tables. That is, we calculate least cost paths and then put that information into routing tables, and then when we have a packet to send, we look at the destination of that packet, look up the routing table to determine the next node to send to. So same as fixed routing there. The difference is that we now regularly update information about the network and regularly recalculate the routes, the least cost routes. We do that on a continuous basis. So for this to work, we need to collect some information about the network. With fixed routing, we just do it at the start, but now we need to continually collect information. And there are different ways to do that. Like we've mentioned in the different design decisions, we can collect local information, just information. Node 1 just collects information about the links that it's connected to. Except the problem with that is that we don't know much about the rest of the network. When we have 100 nodes here, we only have a viewpoint of a very small portion of the network. Another approach, ask your neighbours, your adjacent nodes. Ask node 4 about its links. So node 1 has a larger view of the network information. And the full approach, ask all nodes. Ask each node about their current status of their links and collect that information, and from that information update the least cost routes. Compared to fixed routing, we can get improved performance in that we can more often choose the optimal paths. If the cost of this path, so initially node 1 has a path, has a routing table. Let's put that back, make it a bit bigger. Node 1's routing table. Destination, next node, the least cost path initially from this information from node 1 to node 2 is direct to node 2, the next node is 2. From node 2 to node 3, the least cost path is 1, 4, 5, 3, therefore the next node is 4. From node 1 to node 4, the path is node 1 direct to node 4, so the next node is 4. Node 1 to node 5, the path is 1, 4, 5, so the next node is 4, and similar for 6. That's our routing table for node 1, given this information. But of course, the network changes over time. As people use the network, the costs may change. So if the cost represents the delay of sending packets across this link, if more nodes start sending across this link, then maybe the cost goes up. It goes up to 10, for example. It starts to become overloaded. With fixed routing, we'd keep sending our packets to node 6 via this path. With adaptive routing, what we do is we collect information from other nodes in the network to learn that the cost of this link has gone up. If we use local information only, node 1 would not learn about this change in the cost. From the local information, node 1 only knows about its 3 links to nodes 2, 3 and 4. It doesn't know about the link from 4 to 5. But if we did something else and node 1 asked, maybe every minute, sends a special packet to node 4 saying, what are the costs of your links? Node 4 sends a packet back saying, the cost of my links, and the cost of my link from node 4 to 5 is 10. As a result, node 1 now has an update of the cost of the link from 4 to 5 and can recalculate the least cost paths. It would recalculate and find that the path to 6, 1, 4, 5, 6, has now gone up to 13. And it's not the least cost path, and would update its routing table. At least these two would be updated. Possibly it would find an alternate path. I don't know what it is. Maybe it's 1, 4, 3, 5. In fact, we still get the same next node here. Not a good example. But the path will be different. The cost will be different if we also store the cost. If this one went up as well to 13, then a possible path could be node 1 to 3 to 5. So this next node would change to 3. So we update our routing table as the least cost paths are updated. And we continually do that. We continually ask our neighbours, tell me about the status of your links. And as they change, we continually update our least cost paths and hence our routing table. Therefore, we use the optimal paths more often than when we do in fixed routing. Of course, another approach is we don't just ask the adjacent neighbours, we send a message to all nodes asking them about their links. That's when we have a larger network. If we just ask our neighbour nodes, we only get coverage of a small portion of the network. If we ask all nodes, we learn about the entire network. So that's adaptive routing. Improved performance because we can potentially select the optimal paths more often. The disadvantages are it's more complex. That is, the algorithms needed to select the best path need to take into account the continually updating information. And there's a trade-off between the amount of information and the frequency that we collect the information and the overhead. The more information we collect and the more often we collect, we get better quality information about the network status, and therefore we'll select the more optimal paths. But to collect the information, we need to usually send packets to neighbours. Every 1 minute I send a packet to my neighbours asking them about their links, and the neighbour responds. Not just does node 1 do that, but every node does that, sends a packet to their neighbours asking about their status of the links. As our network grows, the number of packets we need to send in the network to exchange this information grows. And the overhead, that is the amount of packets sent for exchanging information about routing, can be quite significant. So we want to minimise the overhead by not sending so much and not sending to so many nodes, but we'd like to maximize the quality of the information by sending more and sending more often. So there's a trade-off we have to make there. In most practical networks today, adaptive routing is used. Only in small fixed or stable networks is fixed routing appropriate. I think someone answered the question yesterday. So with our fixed routing, if we use this case, exchange status information with all nodes. Let's say every 1 minute, node 1 sends a message to all nodes saying, what are the status of your links? Every node responds. A better approach is quite simply node 1 every 1 minute sends to all nodes a packet saying, this is the status of my links. And every other node sends to all nodes saying, this is the status of my links, some status update. And as a result, if everyone sends a packet to all other nodes every 1 minute, then every 1 minute, on average, node 1 will receive these status updates from other nodes. It will learn about the status of the links of the other 5 nodes. The question is, how does one node send a packet to all nodes in the network? What do we do? Node 1 wants to send a packet that reaches all 5 other nodes. How do we do that? Simpler, give a simpler way. A simple approach is node 1 sends a packet to all its neighbours, which in this case are 2, 3 and 4. And then when those neighbours receive that packet, they send a copy to all of their neighbours. So 1 sends a packet to 2, 3 and 4. 4 receives that packet and simply copies that and sends it to 5, 3, 2, worst case also to 1, but it doesn't need to send back to 1. Similar, 2 received a packet from 1, sends a copy to its neighbours. And when they receive a copy of this 1 packet, they send to their neighbours. And eventually everyone will receive a copy. And this is strategy 2, flooding. And this is a case of getting data from source to destination without caring about the cost of links and without knowing about the other nodes in the network. So we don't need any other information about the network to perform this routing. So instead of choosing a route before sending data, just send the data to everyone. That's flooding. The other approach is, if I wanted to send data to node 6, I choose the route to take and then send it along that route. With flooding, if I want to send a packet to node 6, or if I want to send a packet to every node, I simply send to all of my neighbours. My neighbours will send to all of their neighbours, and eventually node 6 will receive a copy. So that's flooding. It's very simple, but we'll see it's very inefficient. There's a lot of packets sent just to get 1 packet to node 6. Let's see how it works. Well, quite simply, a copy of the original packet is sent to all neighbours of the source. Everyone who receives that packet makes a copy and sends to all their neighbours. There are some exceptions or some rules that we can use to simplify it or to reduce the overhead. The first one is, don't send back to the node that just sent to you. Node 1 sends to 2, 3 and 4 because they are the neighbours of 1. Then node 2 sends to its neighbours. But there's no point in sending directly back to node 1 because node 1 just sent a copy to 2. 2 doesn't need to send back to who sent the packet to it. So node 1 sends to its neighbours, and then node 2 sends to its neighbours except node 1. Similar, node 4 will send to its neighbours except back to node 1. That's the first extension. And we'll always use that case. There's no need to send back to the person who just sent it to you because you know they have a copy. The goal is to get a copy of the packet to the destination. Another, let's jump to extension 4 because in the examples on the next slide we use it first. One extension is to introduce a hop limit in the packet that we send. Inside the header of the packet we include a special value, let's call it the hop limit or a hop counter, that limits the number of times we'll send this packet in the network. A hop limit of 2 means that the packet will only traverse 2 hops from the source. How it works is that at the source we set the hop limit, let's say to 2. We send it to our neighbours. They reduce it to 1. They decrement the value down to 1. If it's not 0, they send it to their neighbours. They reduce it down to 0. When it's 0, do not send to your neighbours. It's a way to limit the number of hops this packet goes through the network, to reduce the overhead. We'll come back to the other extensions through our examples. Here's an example which uses just the first case. It will not send back to the neighbour, to the previous node, and it will use a hop limit. In this case, node 1 has a packet. It has one data packet to send to node 6. We're using a hop limit of 3. And what the diagram shows is that node 1 takes a packet and it makes 3 copies of it. It makes 3 copies because it has 3 neighbours, 2, 3 and 4. The number inside this packet on this diagram is the hop counter, initially 3. So node 1 sends a copy to its 3 neighbours. And what I'll do is keep track of the number of packets which are sent. In fact, it's on the handout I gave you. Where is it? On this handout, on the right-hand side, I'm going to record some of this information on the board. So we're going through this case here. We're using flooding, a hop limit of 3 and no sequence number. What I'm going to show is who sends the node, who they send it to, the destinations, and the number of packets they send. So I'll record it on the board. The first step is the source sends a copy of the packet to its 3 neighbours. So 1 sends to 2, 3 and 4. We're going to keep this simple and say that when we send a packet across a link, it arrives at each of the destinations all at the same time. In real life it may be different in that when I send a packet to 2, it may arrive slightly before the packet I sent to 3 arrives because the delays across the links may be different. But just for this example, let's say I send the packet all at the same time and each packet arrives at the destinations all at the same time. So send 1 copy of the packet to 2, 3 and 4. Let's focus first on node 2. Node 2 receives a packet. Node 2 has received a copy of this packet. They decrement the hop counter. It was 3, they reduce it down to 2. And then they send a copy of the packet all to their neighbours. except back to 1. So node 2 will send a copy to 3 and 4. Similar, node 3 received a copy of the first packet and will send to all of its neighbours. The neighbours of 3 are 2, 4, 5 and 6. Of course it doesn't send back to node 1 because node 1 just sent it. So 2, 4, 5 and 6. Now another assumption we're making here is that, as you'll see what happened, 2 and 4 receive packets at the same time. And then 2 sends to its neighbours, which includes 3, and 3 sends to its neighbours, which includes 2. So you can think that they send like this past each other. So they both send to each other. Again, in real life, that may not happen because of different delays in the network. Node 4 received a copy of that first packet and sends to its neighbours. It doesn't send back to 1, it sends to 2, 3 and 5. And that's what's shown in this slide. Note that the hop counter in those packets is 2. It was reduced from 3 initially. This is just a copy of the one original packet that node 1 wants to get to node 6. They're all copies. And then we can go on and see who receives those packets, and then they send to their neighbours. So the next, let's say the next phase, let's look at node 2. Node 2 has sent packets. Node 2 is also going to receive packets from 3 and 4, because we see 3 and 4 sent to node 2. So node 2 will receive packets. And when it receives a packet, it sends a copy to all of its neighbours again. So 2 will send, and in this example, 2 receives a copy of the packet from 3, and therefore will send to its neighbours, which will be 1 and 4. But 2 also receives a copy of the packet here from 4. So we'll send to its neighbours 1 and 3. That is, in this phase, node 2 receives 2 packets. One is from node 3 and the other is from node 4. Whenever it receives a packet, it simply copies that packet and sends to all of its neighbours except the node where it came from. So from the packet from node 3, send to 1 and 4, that's here, and for the packet from node 4, send to 1 and 3. We already, hopefully you see that there's some waste going on here. There's no need to send the same packet to node 1 twice. Okay? That's what's happening here. 2 sends a copy to node 1 and then sends the same packet to node 1. That's wasteful. In fact, there's no need to send it to node 1 because in fact we received it from node 1 at the start. So, although we'll not go through it yet, we'll see later that there's some extensions to introduce sequence numbers so that we do not send it again. We'll come back to that. Let's go through this case. 2 will send to 1, 4, 1 and 3. What I'm trying to do is count how many packets we need to send in the network. Three in this phase received from 2, 4. So for the packet it receives from 2, it sends a copy to 1, 4, 5 and 6. And for the packet that 3 received from 4, it sends a copy to 1, 2, 5 and 6. and node 4 receive packets from 2 and 3, and therefore sends to its neighbours. 1, 3 and 5, and from the packet from node 3 it will send to 1, 2 and 5. Node 5 received 2 copies of the packet from 4 and 3, so sends to its neighbours. Node 5 received a packet from node 3, so will send to 4 and 6. It will also receive a packet from node 4, so we'll send to 3 and 6. Anyone else? Have we missed one? Node 6 receives a packet. 6 is the destination. It doesn't resend. Inside the packet is the destination address. It says node 6. When 6 receives it, there's no need for it to resend the packet. Okay. I think we've got them all. And those packets that are sent are shown in this slide. And note the hop counter is 1. It was 2 before, we reduced it to 1. So what it's showing, for example, node 4 sends 2 packets to 1, that's here, 1 and 1. 1 packet to 2, 1 packet to 3, and 2 packets to 5. So this 6 packets here is this 6 that I've written on the board. That's all. And similar for the other nodes. This information is in the handout, okay? Don't copy it down, you have it. It is here, okay? Slightly different ordering, but 2, 3, 4, 5 is the 2, 3, 4, 5 here. And the total number of packets, just the count of these. And has the destination received the data? Yes. In fact, the destination received the data here. And it received copies of the data here. So in this case, we've achieved our goal of getting the data to the destination. Will we send any more packets? Why not? One's going to receive packets, 3's going to receive packets, they're all going to receive more packets. Will they send any more? So for example, 3 is sending a packet to 4. Will 4 make a copy and resend? It's either yes or no, not maybe. No, because it's one left. In the packet here, 1 means the hop counter. When each node receives this packet, it decrements it. It's now 0. We do not send on if it's 0. We discard the packet. So we've reached our hop limit. Initially, we had a hop limit of 3. That was chosen by node 1. The idea is that it will only be sent 3 times. 1, 2, 3, for example. So after it's been sent 3 times, do not send it anymore. So we'll send no more packets. So in this example with flooding, to get a packet, one data packet from node 1 to node 6, we actually transmitted 34 packets. If you add up all those transmissions here. So in our network, to get one data packet from source to destination, we had to transmit 34 different packets. There was no routing. That is, we did not choose paths at the start. We just followed the procedure of send to our neighbours. We didn't have to set up routing tables. We didn't have to discover any information about the network. We just send to our neighbours. So very simple. But the problem is, to get one data packet to the destination, we have to send many packets. It's a large overhead of getting data to the destination. If we used shortest path routing, How many packets would we have to transmit in the network to get data from 1 to 6? In the best case, if we use least cost routing in our, this network diagram is the one we have on our board, on the board here. How many packets would we send if we used least cost routing in this network from 1 to 6? How many?
77.
No. If we're using not flooding, using adaptive routing, for example. Using adaptive routing, and we've calculated routing tables, we want to send a packet from node 1 to node 6. How many transmissions in the network? Which path will the packet take? 1, 4, 5, 6, the least cost path. So we have 1, 2, 3 transmissions of that one packet in the network. 3 packets transmitted. To get the one data packet from source to destination, if we use least cost routing, if we had already discovered the routes and created the routing tables, there would be 3 transmissions in the network. If we use flooding, where we don't have any routing tables, we need to have 34 transmissions in the network. That's very inefficient. The 10 times as many transmissions in the network just to get that one piece of data from source to destination. Of course, in shortest path routing, we've omitted the fact that we have to discover the routes. That also requires some transmission of packets. But it's not done all the time. If I have 1,000 packets to send from node 1 to node 6, with shortest path routing, I discover the routes, and then for every packet, there are 3 transmissions. With flooding, for every of those 1,000 packets, there are 34 transmissions. So 34,000 transmissions. So flooding is very inefficient. We have to send many packets in the network to get to the destination. Everyone can flood, can calculate how long it takes to receive a packet, how many packets are transmitted in the network, and at least understand the basic concepts. Send to your neighbours. We can be better than this example. That is, we can reduce the number of packets sent and still get the data to the destination. What if we reduce the hop limit to 2? How many packets sent if we reduce the hop limit to 2? We'd follow the same procedure as here. You think this is the first hop, and these 3 are the second hop, and these are the third hop. So here we had a hop limit of 3. If we had a hop limit of 2, we would end after these transmissions, because the first hop and then after the second hop, and then we stop sending. So reducing the hop limit, we will reduce the number of packets down to, here if we add them up, 12 packets. Did the destination receive the packet? Yes. Yeah, node 6 received a copy of the packet. That's our goal, to get 1 copy of the packet to node 6. With a hop limit of 3, yes, 6 received a packet, in fact many copies. With a hop limit of 2, 6 receives a packet, and we've got less transmissions in the network. That's better, in that we don't have to send packets so often, so many packets to get the data from source to destination. Hop limit of 1, even better. Only send 3 packets. What's the problem? It doesn't reach the destination, so that's a case of incorrect routing. There's no good sending our data, and if it doesn't reach the destination, that's not what we want. So reducing the hop limit can reduce the number of transmissions, But if we reduce it too far, the destination may not receive a copy. Less nodes receive a copy. That's the problem there. Introducing a sequence number in the packet also helps. In our example, we sent packets to 2, 3 and 4, and then they sent to their neighbours, and then they sent the same packet again. And in some cases they sent it twice. Node 3 sent 2 copies of the packet to node 1. That can be wasteful. By using a sequence number, the source creates a packet and includes a sequence number in that original packet, and the same sequence number is in every copy of the packet. If you receive a packet that you've previously sent, do not send again. There's no need to send it again if you've already sent it. That's the idea here. And that can reduce the number of packets transmitted. And on the handout that you have, I have one last example with that. So the top here is with a hop limit of 3, then a hop limit of 2, then a hop limit of 1 with no sequence numbers. If we introduced a sequence number such that if we've already sent this packet, don't send it again, with a hop limit of 3, there's only 13 transmissions needed. Much better than 34. And node 6 still receives copies of the packet. So sequence numbers are typically used in flooding. That's the basics of flooding. Send to everyone by sending to your neighbours, and your neighbours send to their neighbours, and so on. And eventually, if we have a suitable hop limit, the destination will receive a copy. And that's our aim. If we have a no hop limit, that is an infinite hop limit, we can send as many hops as we like, then when we send our packet through the network, it will traverse all possible paths or all possible routes through the network. You can think if we do flooding through this network, a copy of the packet will go in this path, all possible paths to the destination. That can be an advantage or a useful feature because one of those packets will take the minimum hop path. If a packet traverses all possible paths, one of them must be the minimum hop path. We can use that for things like setting up a virtual circuit, choosing a path with the least number of hops. So that's a useful feature with flooding. Another thing is that all nodes are visited. What that means, I send a packet using flooding, eventually everyone will receive a copy. So flooding is useful if you want to distribute information to many people, not just to one destination, but to all nodes in the network. So flooding is useful in that case, especially in adaptive routing. In adaptive routing, we want to get status updates. So we want to know information about node 6, node 5, 3, 2 and 1. So what they do is they flood messages through the network saying what is their current status. Everyone will receive a copy. And as a result, everyone will learn about the current status of the other nodes in the network. And then the node 1 can update its routing tables. So flooding is commonly used to distribute information through the network to all nodes. It's simple. Okay. Problem, it's very inefficient. We need to send many copies of a packet to get one from source to destination. We can use a hop limit to increase the efficiency, but sometimes if we use a hop limit too small, the packet won't reach the destination. That's a problem. there's another variation, selective flooding. With flooding, I send to all my neighbours. Selective flooding, select some of your neighbours and send a copy to them. Okay? And there are different ways to select which neighbours. Maybe it's random. Today I select these 3 neighbours out of my 4 neighbours. 1 minute later I select a different 3 neighbours. Or maybe there's what's called round robin, where I select these 2 neighbours first, and then these 2, then these 2, and then come back to these 2, and just keep taking in turns of selecting which neighbours to send to. And there's different variations of selective flooding. The idea is that we reduce the number of packets sent. Instead of sending to all neighbours, send to just say 2 of your 3 neighbours, less packets sent, better efficiency. But the problem may be if you select the wrong neighbours, the packet may take a long time to get to the destination. And it may not get to the destination if we use a wrong hop limit. So selective flooding, by not sending to all your neighbours but just a subset of your neighbours, can increase the efficiency, but it can increase the time it takes a packet to get to the destination, and in some cases increase the chance that the packet won't get to the destination. So that, again, some trade-offs in using that. That's flooding, and that's routing in switched networks. Quite quick through flooding, but the concept is quite simple. Send to your neighbours. Your neighbours will send to their neighbours, with some exceptions, like don't send back to who sent it. Don't send it if you've already sent it previously using sequence numbers, and limit the number of hops. So some ways to reduce the number of transmissions. Any questions on flooding and or routing and routing tables before we finish this topic? Yep. Yeah, the primary difference between adaptive and fixed routing is how often we update the information. That's all. Fixed routing, we don't. Adaptive routing, we do. So in fact, other than that, the way that we use routing tables is the same.
Can you explain sequence numbers again?
Sequence numbers in our flooding case. Let's give an example. Source node creates a packet, has some data, has a header. In the header there's a source address, N1, destination address, N6, hop counter, hop limit. In our example, initially 3, that's chosen by the source. And let's say we also include a sequence number. So the first piece of data they send, they give sequence number 1. Node 1 sends to its neighbours. So 2, 3 and 4 receive a copy. They all reduce the hop limit, or the hop counter, down to 2. So they make copies of the packet, reduce the hop counter down to 2. The sequence number stays the same. The sequence number counts the sequence of the data. So when, in this example, the sequence number is always the same. So how we use that, 2, 3 and 4 receive a copy. They send copies to their neighbours, as shown here. Okay. As a result, 3 sends a copy of that packet with sequence number 1 to 4. 4 has sent a copy of that packet with sequence number 1 to 3. So the sequence number is the same as the original packet. Now in the next phase, 4 has received this packet, but 4 received that packet previously from 1. So simply discards it. So in the first phase, 4 received a copy of the packet from 1. Then it receives another copy of that same packet from 3 and also from 2. It discards those two copies. How does it know it's the same packet? The sequence number. Okay, that's all. Sequence number is used to know that this packet is the same as a previous packet. When I have more data to send, so new data, I create my packet, header, some new data to send from node 1 to node 6. I set the hop limit, and I may change the hop limit. Maybe I change it to 2. I don't have to. And use the new sequence number. That's for a new piece of data. In the diagram here, these are copies of the original data, so all have the same sequence number. Any other questions? I think you can try or think about selective flooding examples. Essentially
What does sequence number mean?
Sequence number is the sequence of the data. Let's say I have a large file to send to node 6. I break it into 1,000 packets, 1,000 data packets. The first packet I give sequence number 1, the second packet sequence number 2, third packet sequence number 3. With flooding, I send packet with sequence number 1 to my neighbours. They copy that packet. So the copy will have the same sequence number, except the hop counter will be reduced. So the copy of the packet, which is shown in these diagrams, these are copies of the original packet. The only thing that changes is the hop counter. The sequence number stays the same. So node 4 sends the packet with sequence number to all its neighbours, sequence number 1. Eventually, node 6 receives a copy of that packet with sequence number 1. Sometime later, because I had a large file to send, this was just one part of the file, I send more data. Well, that has sequence number 2, and so on. And it can be used to distinguish or to know whether you've received and transmitted a copy before. Because if you received packet with sequence number 1 and have sent it to your neighbours, and then sometimes later you receive packet with sequence number 1 again, you know you've sent packet with sequence number 1 to your neighbours before. Do not send to your neighbours again. So there's no need to send to your neighbours again because you've done it recently.
So if we the different sequence number, they send
Different sequence number you treat independently. That is, if I receive a packet with sequence number 2 and I've never received that before, that sequence number, then I'll send to my neighbours. If I receive sequence number 2 again, I will not send to my neighbours. Okay. The remaining slides we're not going to go through. We've done adaptive routing. This routing protocols and algorithms gives an example of a simple or a basic routing protocol. You will cover routing protocols, all these acronyms, next semester in computer network architectures and protocols. That's when you'll cover details. We've covered just the concepts. The details of how real routing protocols work, you will cover next semester. So let's finish. And this is a summary of the two topics of switching and routing, because they're related. In fact, generally networks. Now we have communication networks formed by connecting devices across multiple links. Switching is the method for delivering the data through the network. we send to one node that switches out to one of its links. It chooses a link and it sends there and so on. The stations, the end user devices, PCs and so on, are the sources and destinations of data. The switches typically just forward data. They are not generating new data. We've covered there are two general approaches for switching, circuit switching and packet switching. And inside packet switching, there's virtual circuit packet switching and datagram packet switching, so really three approaches in total. Routing is the way to find the path from source to destination. Switching is delivering the data across that path. And in routing, there are different metrics, ways to measure the cost, different strategies we've looked at, adaptive, flooding. There are different algorithms for calculating the least cost path, Dijkstra, Bellman-Ford and others. And you'll see next semester there are many different protocols to implement these strategies and algorithms. So what is the exact format of this packet? Well, it depends upon the different protocols in use. In practice, circuit switching developed for telephone networks and is still used in telephone networks and some private data networks. Packet switching was developed to be more efficient when we have data, not voice calls, but web traffic and so on, transferring files. And it's used in the internet. Our next topic's about how the internet works, and that's where packet switching is used, in particular datagram packet switching. Most large networks use adaptive routing. Some routing algorithms or least cost algorithms, Dijkstra and Bellman-Ford, you've heard of in other courses. The main trade-offs of which routing approach is best depends upon how big the network is. Is it 10 nodes? Is it 1,000 nodes? How much traffic or how many packets are being sent through the network? Is it just traffic from SIT users, or is it the data from all the people in Bangkok being sent through the network to other countries? And how often that changes, the network and the traffic. The more stable the network, the easier it is to get updates. The more dynamic, we need to get updates more often. The next topic is on how the internet works. We will say a little bit about local area networks, but we will not go into detail because you did that in the assignment, at least wireless local area networks. So you all know about LANs from the assignment. So we'll summarise LANs next week and then start on the topic of the internet protocol.